So in this section, we're going to go over absolute convergence and then two tests, which are the ratio and root test. So the ratio test and the root test are some of the most important tests we're going to learn about series, and they're going to be really useful in the upcoming section. So they're very simple, very straightforward. The really nice thing is you don't have any hypotheses you have to satisfy. You get to just jump straight into the test. But they are really powerful, so we have another concept we have to go over, which is called absolute convergence. So the idea is if you start with any series which has a general term, an, and you look at all of those terms in absolute values, so you're looking at the sum from n equals 1 to infinity of the absolute value of an. So instead of the terms you had before, you're now assuming that every single one of them is positive. So if you think if it's an alternating series, then it's going to kill that alternating terms. If you had some negative and some positive, now everything is going to be positive. So the idea of absolute convergence is you can say a series is absolutely convergent if in absolute values that new series you get is also convergent. So let's look at a simple example. We want to see, is this series absolutely convergent? And our general term is negative 1 to the n times 14 over n to the 6. So what we want to do is we just want to look at that term in absolute values. And all that's going to end up doing, the 14 and n to the 6 are both positive, so this alternating part we have is going to disappear. So this just becomes the sum from n equals 1 to infinity of 14 over n to the 6. And you just pull that 14 out, and what you're left with then is a p-series. So you have a constant times a p-series. But since that has a power that's 6, which is greater than 1, we know it's convergent. So in absolute value, this series converges. So we can say that the sum from n equals 1 to infinity of negative 1 to the n times 14 over n to the 6 is absolutely convergent. So you could have gone and applied the alternating series test to this, but you don't really need to because absolute convergence is much stronger. You're taking something that could be alternating and now assuming everything is positive, showing that's convergent. We're going to see that it's going to make the original series we start with convergent as well. So let's look at another example of something that's not absolutely convergent. So we showed that the alternating harmonic series is convergent. The general term for this was decreasing when you ignore the alternating part. That limit went to 0. We used the alternating series test to show this. Okay. But if you look at it in absolute value, when you destroy the alternating part, it's the harmonic series, which we know is divergent. So the alternating harmonic series is not absolutely convergent. Okay? So this is a concept that's called conditional convergent. So a series, which is an, is conditionally convergent if it's convergent itself, but not absolutely convergent. So kind of the main difference between these two examples is when you look at this series, we know it's convergent by the alternating series test. When you look at it in absolute value, it's not convergent. If you were to go back to this first example, in absolute value, we do get something that's convergent. And if you went through and applied the alternating series test to this one, it's convergent as well. So absolute convergence is really powerful and much stronger. Okay? So basically, if you're looking for an example of something that's conditionally convergent, that would be the alternating harmonic series. The alternating harmonic series is convergent, but it's not in absolute value. Okay? So this is a theorem that really kind of sums up how powerful this absolute convergence is. If a series is absolutely convergent, then you know it's just this normal convergence that we've dealt with before. And we're going to go through a proof of this because it's pretty short and it just applies the comparison test for it. So what we want to do is we want to end up coming up with a bound, and we're going to be able to rewrite things a little bit. So if you think of this term an, it's possibly positive or it's possibly negative. So if you add the absolute value of it, if they're both positive, you would get 2 times the absolute value of an. If this is negative and this is positive, when you add them together, they're opposite signs, you get 0. So you can bound an plus its absolute value between these two quantities. So the reason you can do that is because the absolute value of an is either exactly this back or it's the opposite. So they're going to cancel out, or you're going to just double what's going on. So if you know that the sum of an is absolutely convergent, then when you add those absolute values, it's also convergent. So if you take 2 times it, it's also convergent. So pretty much by the comparison test, when you sum this up, the sum of 2 times an will be a convergent series. So that means by the comparison test, this term is positive. So when you sum this up, it's also going to be convergent. Okay? So by the comparison test then, because this term is trapped between 0 and something convergent, you get that it is also a convergent series. So I now know the sum of 2 times an is convergent. I know the sum of an is convergent, and I know that this is convergent. So what we can actually do is rewrite just our original term we started with to get that it's normally convergent. So since the sum or difference of 2 convergent series is also convergent, we can rewrite the original series as the term itself plus or minus the absolute value of the term. So those two would just cancel each other out. So we're adding and subtracting the same thing. So now we can split it into 2 separate pieces. This first one we've seen as convergent by using the comparison test, and we assumed that our series is absolutely convergent. So these sum and differences make us have a convergent series. So the original series we started with is also convergence. So if you have something as absolutely convergent, you get the regular convergence we've dealt with so far for free. Right? So it's much more powerful. If it's absolutely convergent, it's convergent. If it's not, when you have that -1 to the n involved, it might make it something that's conditionally convergent. Okay? So let's try some examples. We want to determine whether the series is absolutely convergent, conditionally convergent, or divergent. And our general term is going to be sine of 4n over 4 to the n. So we have a bit of a problem. You want to do this with absolute convergence. It might be natural to want to kind of use a comparison test maybe, or a limit comparison, because this doesn't do a whole lot. So it looks like a geometric series. But because we want to deal with absolute convergence, I need to take the absolute value of that general term. But the really nice thing is when you look at sine of 4n in absolute value, you know that's bounded above by 1. So this is going to be less than or equal to 1 over 4 to the n. And if you look at the series with the general term 1 over 4 to the n, that's just a geometric series. Its common ratio is 1/4. So in absolute value, it's less than 1. So it's convergent. So now I have, when we sum this series up, it's convergent. I know these terms are positive, and they're smaller than a series that is convergent. So we get, by the comparison test, the series with the absolute value of sine of 4n over 4 to the n converges. So in absolute value, it converges. So you can say the series is absolutely convergent. So yes, this series is absolutely convergent. And if you went to apply the comparison test on the original one, then you'd be able to see kind of the same thing. But you would run into a bit of a problem because you would have to show that sine of 4n is always positive, and that was a little bit tedious to do, and you probably can't actually even do it. So absolute convergence is going to be better for us. Okay? So this leads into one of the nicest tests we possibly have, which is the ratio test. So you do exactly what it says. You're going to take a ratio. And basically what happens to that ratio will dictate whether the series is convergent or divergent. So the first part of the ratio test tells you if you take the limit as n goes to infinity of the absolute value of an plus 1 over an, if that equals L, which is less than 1, then the series is absolutely convergent. So then it's normally convergent. If that limit equals L, which is bigger than 1, or it ends up going to infinity, then you get the series is divergent. And then you have a bit of a cutoff point. If this limit equals 1, the ratio test is actually going to fail. So you won't be able to say anything about the series being convergent or divergent. So in that case, if it fails, you have to try a different method. But the great thing about this test that you can see, there are absolutely no hypotheses. All it does is it tells you to look at this limit. Based on that limit, you get absolute convergence, you get divergence, or you're going to get that it's inconclusive. So you have to try something else. Okay. So pretty much the idea of the proof, just so you can kind of intuitively see why this happens. For the first one, if this limit goes to something smaller than 1, that means the n plus 1 term is smaller than the term before it. So these terms are just getting smaller and smaller, and they're doing it pretty quickly. So that's an idea. It's going to 0 quick enough, it'll be convergent. In the case that the limit equals L, which is bigger than 1, that would mean the n plus 1 term is bigger than the term before it. So these are just getting bigger and bigger and bigger and bigger. So it's not going to end up being something convergent. You're going to sum up something over and over and over and over again, and something non-zero. And the same idea applies if this limit equals infinity. Then those terms are just excessively getting bigger. In the case that it fails, then they're close in size. So basically, if this ratio equals 1, they're similar, but you just don't know whether that means they're small values or they're large values. So if you try any type of p-series with the ratio test, it's going to end up failing. So if we look at a simple example, if you sum up from n equals 1 to infinity of just n, that's definitely divergent. 1 plus 2 plus 3 plus 4 plus 5, just getting bigger and bigger. If you try to apply the ratio test, you get the limit as n goes to infinity of n plus 1 over n, which is 1. So this one's clearly divergent. So if we go ahead and we look at a different p-series, which you know is convergent, so the value of p is 2, which is bigger than 1, this limit still goes to 1. So in one instance, we have convergence over here, but the ratio test fails. And in this other instance, we know this is divergent, and again, the ratio test failed. So both of them equal 1. So in the case you get 1, you can't do anything. You have to apply to a different test. So one of these converges while the other diverges, but they have the same limit. So you're not able to say anything if that limit equals 1. Okay? So the main kind of thing you want to recognize when you want to use this test, first, if you're asked about absolute convergence, then you probably want to try the ratio or likewise the root test. And in both of these tests, there's going to be absolutely no hypotheses. But the key distinction for when you're going to use the ratio test is you're going to see factorials. Because when you take a ratio, things are going to cancel really nicely. You can directly take the limit and then apply a conclusion. So you don't have to satisfy any hypothesis. Okay? So let's try an example together. We want to determine if this series is absolutely convergent, conditionally convergent, or neither. So basically, if we try absolute convergence and that ends up failing, there's a good case that it'll be conditionally convergent. So that would mean that you'd apply like the alternating series test to it. So one thing I kind of want to refresh just real quick up here, if you don't remember factorials, n factorial is you take n and you multiply it by every single integer before it, all the way down to 1. So you keep going, times 3, times 2, times 1. So if you look at a specific example with a number, like 3 factorial is 3 times 2 times 1, 5 factorial is 5 times 4 times 3 times 2 times 1. And the nice thing is, if you notice, if you take off this 3, you're left with 2 times 1. That's the same thing as 3 times 2 factorial. Over here, you've got 5 times 4 times 3 times 2 times 1. So this is 5 times 4 factorial. You can always pull off the top integer and get the next number factorial. You could even write this as 5 times 4 and then pull off the 4 and get 3 factorial. So it's a really nice property with what's going on. Okay? So let's try this together. Our indication that we're going to use the ratio test is we have these factorials. So the first thing we're going to do before I take this limit is we're going to have to simplify that expression an plus 1 over an. So let's go ahead and work with this and try to simplify it as much as we can. Okay. So we need to take the n plus 1 term. So all you do is anywhere you see an n, it's going to get replaced by n plus 1. So I'm going to have 2 times n plus 1, that number factorial, divided by n plus 1 factorial, and that's going to be squared. And you're dividing it by exactly this term, so just multiply by the reciprocal. So this is times n factorial squared over 2n factorial. So you want to be careful. If you notice, I didn't write it like this, because this would indicate you're taking 2 and you're timesing it by n plus 1 factorial. So you need the number with parentheses around it times the factorial at the end. Okay? So now we want to go ahead and manipulate this. What I'm going to recommend doing is grouping the like pieces. So we've got this 2 times n plus 1. That's really 2n plus 2 factorial. And the piece that was similar to it is the 2n factorial. Okay? Now in the top, I have n factorial squared. So that's n factorial times n factorial. And in the bottom, the ones that are like are the n plus 1 factorial squared. So you get n plus 1 factorial times n plus 1 factorial. Okay? So what I'm going to do is I'm going to work with the work with the factorial that's bigger. So this 2n plus 2 is a larger number. I'm going to keep pulling off the top integer, get the next one factorial until it'll cancel with the smaller one in the bottom. So if you pull off the 2n plus 2, you're left with the next number factorial. So 1 less than that would be 2n plus 1. And you could get factorial, but that's not going to cancel with what we have in the bottom. So I'm going to go one more time. If you pull off one more, you'd get 2n. So you subtract 1. And so you'd get 2n factorial. So I've pulled off the top two integers. And now what happens is these 2n factorials cancel. And I'm just left with the 2n plus 2 and the 2n plus 1. Now we're going to do exactly the same thing for the next one. If you look, the n plus 1 are the bigger values, so I'm going to pull off of that. So I'm going to leave the n factorials alone up top. And if I work with this first one, you have n plus 1, you'd get the next number factorial. So that would be n factorial. So now we're going to have some cancellation. The n factorials disappear. If I do the same thing with the second one, you have n plus 1, and then you get the next integer, which is n factorial. And again, we have nice cancellation. So what we're left with in the numerator is 2n plus 2 times 2n plus 1. In the bottom, we have n plus 1 times n plus 1. Okay. So I'm going to have to look at this in absolute value, and I'm going to have to take a limit. So I'm going to go ahead and just FOIL this out. I'm going to trust that you can do this. Your first terms are going to be 4n squared. Your outer plus your inner will become 6n. And then the last term is 2. And the bottom's nice and simple. That's n squared plus 2n plus 1. Okay. So we just need to take the limit as n goes to infinity of the absolute value of an plus 1 over an. So you can see it's kind of useful just to manipulate this inside expression first, so I didn't have to write limit before each and every single one of these steps. So this becomes the limit as n approaches infinity of the absolute value of 4n squared plus 6n plus 2 divided by n squared plus 2n plus 1. Okay. But the n's are positive, so this doesn't really matter. This is the limit as n tends to infinity of 4n squared plus 6n plus 2 divided by n squared plus 2n plus 1. Okay. So this is a nice polynomial. It's just going to go to those leading coefficients. So this limit equals 4, which is definitely bigger than 1. So what that tells us is this ratio goes to something bigger than 1. It's going to be divergent. So thus, by the ratio test, the series we started with, which is the sum from n equals 1 to infinity of 2n factorial over n factorial squared diverges. So let's go ahead and do one more example, and then we'll jump into the root test as well. So we want to determine whether the series is absolutely convergent, conditionally convergent, or divergent. And the series we're given is the sum from n equals 1 to infinity of n to the 100 times 100 to the n over a single n factorial. So at first kind of glance, it seems like that numerator is going to be extremely large, but it's going to turn out that the denominator is growing so much faster, this thing's still going to end up being convergent. So the first thing we want to do is we want to look at the an plus 1 term over the nth term. So the n plus 1 term is you have n plus 1 to the 100 times 100 to the n divided by n plus 1 factorial. You're dividing it by an, so just multiply by the reciprocal. So you get n factorial over n to the 100 times 100 to the n. So we're going to go ahead and group the like pieces. Let's do those powers of 100 together. So n plus 1 to the 100 divided by n to the 100, 100 to the n plus 1, forgot the plus 1, over 100 to the n, and then we've got the factorials together. Okay. So in this first fraction, they're both to the same power, so we can write that as n plus 1 over n to the 100. If you simplify those expressions, you get 100 to the n plus 1 minus n, so just 100 to the first power. And then the factorials, the bigger values in the bottom. So let's pull off that top integer, which is n plus 1. And then you get times the next integer factorial. So the n factorials cancel, and we can simplify this one more time. N plus 1 over n simplifies nicely to 1 over 1 plus n to the 100. We have times 100, and then this last piece is 1 over n plus 1. So when you take the absolute value, it doesn't really do anything because every term is positive. So if you want the limit as n tends to infinity of the absolute value of these things, the limit as n tends to infinity of 1 plus 1 over n to the 100 times 100 times 1 over n plus 1, because an absolute value doesn't do anything. So if you think of what's going on in the limit, this goes to 0, this goes to 0. So this is equal to 1 plus 0 to the 100 times 100 times 0. So this thing goes to 0, which is definitely less than 1. So what we can say is by the ratio test, the series, which is the sum from n equals 1 to infinity of n to the 100, 100 to the n, over n factorial, is absolutely convergent. So we get absolute convergence with the root test, and which means it's regularly convergent as well. Okay. So the next test we have is very similar. It's the root test. You get a ratio, you're going to take a ratio of terms. For the root test, you're going to take a root. And really, you're going to take the nth root of the absolute value. You're going to get exactly the same criteria. If that limit is something less than 1, it's absolutely convergent. If the limit is something greater than 1 or it's infinity, it's divergent. If it equals 1, the test is inconclusive. So same exact criteria. You just are now taking the nth root of the absolute value. Okay? So the kind of key is between these two. The ratio test works really well for factorials. The root test is going to be great when you have everything to some power of n. So it's going to fail in the same instances that the ratio test is going to fail. So basically, if you try one, it's inconclusive. Don't try the other. Try one of the previous tests we learned, because it's not going to actually work, right? And then there's one more limit that might be useful that pops up. if you want to take the limit as n goes to infinity of the nth root of n, you can rewrite that as n to the 1 over n. And then we can rewrite that using e's and natural log because they're inverses of each other. Bring the natural log in, so the power comes out, and then technically you can apply L'Hopital's rule, assuming that this n is a continuous variable. So this goes to e to the 0, which is 1. So the nth root of n goes to 1 as n goes to infinity. Okay. So let's try a few examples of this. Same criteria. All you need to do is manipulate that nth root and see what does that limit go to. So the key we want to use the root test here is it doesn't matter what these terms are. We just have everything is raised to some power of n. So that's our indication root test is going to be good. So what we need to do is we need to take the nth root of the absolute value of an. And you don't need to rewrite that root. It's the absolute value of an to the 1 over n. Okay. So we're going to take the absolute value of negative 2n over n plus 1 to the 5n. And then we're going to raise that to the 1 over n power. Okay. So you can always bring that absolute value inside those exponents, so we can kind of switch these. This is the absolute value of negative 2n to the n plus 1 to the 5n power, and then raised to the 1 over n. Okay. So when you go ahead and multiply these out, you have 5n over n. Those end up just canceling. So this becomes the absolute value of negative 2n over n plus 1 to the 5th. Okay. And then all the absolute value does is it gets rid of that minus sign. So this is 2n over n plus 1 to the 5th. Okay. So we want to take the limit as n goes to infinity of this thing. So it's the limit as n goes to infinity of 2n over n plus 1 to the 5th. And again, what happens on the inside is it goes to those ratios of powers. If you want to see a more precise, divide top and bottom by the highest power. So this is the limit as n goes to infinity of 2 over 1 plus 1 over n to the 5th. So this goes to 2 over 1 plus 0 to the 5th. So that's 2 to the 5th, which is 32. That's definitely bigger than 1. So what we can say is this is divergent by the root test. So hence, by the root test, the sum from n equals 1 to infinity of negative 2n over n plus 1 to the 5n diverges. Okay. Let's do one more. Let's determine whether this series is absolutely convergent, conditionally convergent, whatever you want. So you could apply the ratio test. I'm going to show you one more example using the root. Let's go ahead and take the nth root of an. And this is going to be where that special limit comes into play. So this becomes 2n over 3 to the n to the 1 over n power. And so the absolute value does absolutely nothing. So this is 2n to the 1 over n. 3n to the 1 over n. So that's going to make those cancel in the bottom, and you can also split this. This is 2 to the 1 over n times n to the 1 over n. And then in the bottom, those cancel, and you just get to the third power. So when you go to take the limit as n goes to infinity of the nth root of the absolute value of an, it's the limit as n goes to infinity of 2 to the 1 over n to the 1 over n over 3. So 2 to the 1 over n just goes to 2 to the 0. N to the 1 over n we know goes to 1, and this gets divided by 3. So this limit is 1/3, which is definitely less than 1. So we can say by the root test, the series, which is the sum from n equals 1 to infinity of 2 to the n over 3 to the n, is absolutely convergent. Okay. And again, you could apply the ratio test for this, but just another example with the root. So you're pretty much going to jump to using the ratio test first, just because it's a little bit simpler. But in that case, everything is to a power of n. Go for the root test.